target 4.3HE. With this target, we're bringing together everything that we've learned. We're going to compare ionic, covalent bonds, metallic bonds, and one more, something that we call a network solid. Now, a network solid sometimes is also known as a network crystal. After this, you've covered every type of bonding and attractive intermolecular forces that you could see. Now, with a network solid, this is when you have every single atom covalently bonded to each other. So every atom in this structure is covalently bonded. Now remember, covalently means shared electrons to one another or to each other. So there are no intermolecular attractions. Everything has a true bond. Now remember, bonds are strong, where intermolecular attractions are very weak. There are two examples that you need to be familiar with. One is a diamond, and as we have talked about before, a diamond is the hardest structure you're going to find. Okay. A diamond doesn't melt. Okay. As a matter of fact, it will vaporize instead of melting at 3,500 degrees Celsius. Now remember, water melts at 0 degrees Celsius and boils at 100. So just imagine how hot that is. Okay. Another structure would be silicon carbide, which is very much like a diamond. As a matter of fact, it replaces diamonds in a lot of things. They have what they call diamond-tipped drills, which can be very expensive. So sometimes they will replace that with a silicon carbide tip. Silicon carbide, sorry. Okay. Now silicon carbide is still a network solid. Again, crystal structure, just like a diamond, every atom covalently bonded to each other. So you still have those very, very strong bonds. What is the difference? It actually has a melting point of only 2,700 degrees Celsius. Still extremely high, but not quite as high as a diamond. So now what 4.3HE is going to ask you is, they're going to give you a sample. And they're going to say, okay, first of all, what kind of bond is it? Based on, the sample that they're giving you. What do you have? What kind of melting point does it have? What kind of structure does it have? Will it be a crystal? Will it be a liquid? What will you see? So for example, I might say that you have methane. And then I'll tell you what methane is. It's CH4. I would ask you, what is its bond type? Well, we have two ways of describing its bond type. We can use whether it's, what kind of elements have come together, or we can use electronegativity values. Well, I'm just going to use the types. I have two nonmetals, so I can say that my bond type, it's a molecular bond or covalent bond. I don't care which one you use, molecular or covalent, they mean the same thing. Okay, so that's the bond type. We should know their properties. So I could ask you, maybe, is this malleable? Okay, well, methane is a molecular compound. Molecular compounds, if they're solids, are very brittle. So no, it would not be malleable. I could ask if it was a good conductor of heat or electricity. Remember, to have conductivity, you have to have charges that can move. Well, this is covalent. They're sharing electrons. It's not ionic, so you're not going to have moving pieces with charges in it. So no, it is not a good conductor. I can ask you about melting points. What kind of melting point would it have? Well, again, it's a molecular compound. Molecular compounds have very low melting points. Or we could, suddenly go the other way. Like up here, we were just talking about silicon carbide. So I could say you have SiC, silicon carbide. What's its bond type? Well, you got two nonmetals. So you got covalent bonds. Okay. Is it malleable? Well, it's a crystal, a very hard crystal. So no, it's not malleable. Is it a good conductor? Again, not made up of ions. So when you do melt it, it's not going to have any charged particles that can move. So no, it would not be a good conductor. What kind of melting point does it have? Well, this isn't just high. This is extremely high. Okay. And so you should be able to pick out all of these properties based on what they're made of. So we got an example of molecular. Oops, and that's not even covalent. That should actually be a network solid. Well, it's still a covalent bond, isn't it? So I could give you credit for covalent because they're still sharing. What else could we use? Metallic. We talked about metallic bonds. And metallic bonds a lot of times we see as either as alloys. So I could give you an alloy, like I could say that you have brass. Okay, a mixture of copper and zinc, I think it is. Okay, but I know it's an alloy, so I know it. The bond type would be considered metallic. Okay, it's a mixture of metals. Is it malleable? Yeah. Look at what we make things with brass. You can make statues. You can, definitely shape it into things. Is it a good conductor? Yes, because it has metals in it. What is its melting point like? Its melting point is going to be high. Metals have high melting points. Okay, so we're looking at these four things. That's what we're trying to compare when I give you something. So here we've got a metallic, you've got a covalent, also known as a network solid. Here you've got covalent bond or molecular compound. Something ionic. We could have something like table salt, NaCl. You've got a metal and a nonmetal. So what kind of bond would that be? Well, I'm going to have an ionic there. Is it malleable? No. Remember, ionic compounds are crystals. They're going to shatter when you hit them. Okay. Are they good conductors? Sometimes. Remember, if it's ionic, that it's only going to conduct if it's melted or dissolved. And what kind of melting point does it have? High. They have high melting points, greater than 300. So I think I've covered everything here. You've got a molecular compound that has covalent bonds. You've got a network solid that has covalent bonds. You've got an alloy that has metallic bonds. Another example of something like this, maybe I don't give you an alloy, maybe I just say it's copper, and then you know it's metal. So we're looking at what kind of atoms this is made up of. Okay, like I said, I think this is copper and zinc. Now notice I would put a comma in between them to show that it's a mixture. Where NaCl, there is no comma, so I know it's a compound. SiC, it's a compound. Okay. Remember, there are only two types of network solids. That's the diamond and the silicon carbide. If you don't get one of those, that's not what it is. And then to wrap this up, another thing that you're supposed to know is to be able to explain the malleability of a metal and how it's different than that of an ionic compound. And we had talked about that before. When you have an ionic compound, you've got a plus, minus, and minus, plus, minus, plus, plus, minus, plus, minus. If you hit this with a hammer, that's going to shift. So you get minus, plus, minus, plus, minus, plus, minus, plus. And when it shifts, you end up with minus, plus, minus, and those repel. Okay, remember? That causes the crystal to shatter. Okay, it's going to shatter. Where if you have a metal, remember you've got that cation in there, and then you have what they described as a sea of valence electrons. So you have all these electrons around here. that are free to move. When you hammer this, and put a little dent in it, it shifts those, but the electrons are still moving freely and keeping these positives from repelling. So they don't repel, so it doesn't shatter. Okay. And then again, if we go back to your ionic substance like this, you do have pluses and minuses, so as a solid it will not conduct electricity because these can't move. But in a metal, this can conduct electricity because these electrons are all moving. So as long as they're moving, that electricity can flow right through because it can be carried on those electrons. But if you melt this, then these pluses and minuses can move. Or if you dissolve it, the pluses and minuses get broken apart and surrounded by water and then are free to move. And so they can conduct electricity very easily. Most molecular compounds, though, if you go back to like methane, remember they don't have free moving electrons, they don't have ions, so they cannot conduct electricity. You have to have a fully charged particle to conduct electricity.